Videos on non-parametric tests, and sometimes we call those distribution free tests. And as we've talked about with the tests that we've examined so far, there are always certain assumptions that we need to validate. And in certain situations, if we validate certain assumptions, the results can be shown to be robust. For example, violating the normality assumption for ANOVA is not typically a major deal, but nevertheless, there are certain times that we deal with types of data that we just know don't come from a normal distribution, may not have equal variances, and other assumptions that aren't met as well. Now, if you think about when we calculate a p-value, there are just certain assumptions that we make. And first of all, one of the assumptions we make is very important, is we know how the underlying probability distribution is going to behave. For example, if I want to find the p-value of the vertical line there, we should know now that it's the area to the right of the curve. Now, if we're doing a two-tailed test, we've got to account for some area down here too. But nevertheless, the p-value is just area under the curve of the underlying probability distribution. But what if we violated some assumptions and the underlying probability distribution isn't what we think it is? Well, then you can see clearly that in this distribution right here, that the p-value would be different than what we actually would have calculated. So we would kind of think that we're drawing from this distribution, but we're drawing from this distribution, which gives us a situation where our p-values aren't stable, and we could, in essence, we could reject the null or find statistical significance when we shouldn't. Well, enter into non-parametric statistics. And I remember when I first started teaching statistics, before I actually went to grad school and actually learned a little bit, I thought everything was normally distributed. I thought all the distributions were perfect, all of our p-values, everything was fine and dandy. And it turns out that a lot of times in education data that this is not the situation that we have. For example, a lot of data that we collect on humans isn't normally distributed. Data that we collect, ordinal data where we've ranked things, it would make sense that those they don't form a normal distribution. And clearly, anytime we conduct or collect data where we've used the Likert scale, where people will, on a scale of like 1 to 5 will talk about their feelings about a particular topic, we wouldn't expect those to form a normal distribution either. So this is what we're going to do. So okay, so what I want to do in this video is I want to look at the two-sample t-test version of a non-parametric test. So typically we would do independent sample t-test here, but we have underlying assumptions of equal variances and that our measurements came from normal distributions. But let's say we know that that's not the case. Well, what we would do here is called a Wilcoxon rank sum test. Now guys, we take this stuff literally here, okay? The name is extremely appropriate because we actually do rank our data. We actually do sum up stuff and conduct some inference from there. So imagine what we've done is, let's say we've collected data on a Likert scale. My daughter's making breakfast and she is being very, very, very loud. She'll probably be louder now. And let's say that we give people the following. Let's say they have, I don't know, let's say they have 5 possible responses. And let's say that this is strongly disagree, this is disagree, neutral feelings, agree, and strongly agree. Now let's say we come in and we ask a group of people, and we have their ID. So we have the first person, the second person, third person. Let's say we have up to 20 people. And let's say we also have their gender, female, male, whatever it may be. So the first person comes in, we ask them a particular question, and they strongly agree. So we would give this person probably a 5 on that score. The next person comes in and answers the same question, and they disagree. Well, we'll give them a 2. Now, you can kind of think that the responses here, there would be no reason to think that these responses would form a normal distribution. Even if I conducted a histogram or constructed a histogram, and I saw something that looked bell-shaped and symmetric, theoretically, my kind of common sense kicks in, where I'm just not expecting those measurements to be normally distributed. So let's carry out the analysis here, and let me show you how this works. What I've done here is I've actually have a data set here, and these would be the responses from I think it was 7 questions, so there would be a possible of 35 total points. So going back to the Likert scale where we give a point of 1, 2, 3, 4, and 5 over 7 questions, we could add those up for each individual. So this person right here was a male, they had a total of 13. This person right here obviously was a female, they had a total of 16. This person right here must have strongly agreed with everything, because they got of 7 questions, 5 total points, they have 35 total points, which is the most that they could get. Now, the way that we carry this out is we look at the scores. So I'm going to copy these and paste. And then I want to copy and paste the females. So the first thing we do is we look at the scores, put them in order regardless of whether it's a male or female, what group that we have. So we're going to rank our data. So the easiest way to do that would be go up here to data, go to sort, and let's just sort the data. Now, what it's done here is it's sorted the data, put the smallest one first, and so on and so forth. So what I would want to do next is I'd want to come in and do a relative ranking. So this is first position, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Okay, this is boring. But I have to come in and account for ties. So because 13s share the 1 and the 2 position, I'm going to give them a relative ranking of 1.5. Now the 14 shares the 3rd position by itself, so I get give a 13. Now when I get to 15, I've got 3 that shared the 4, 5, and 6, so I'm going to give all those 5s. So really I'm just ranking, just kind of averaging the rank here. If I look at my 16s, I have 4 that were 7, 8, 9. So I'm going to go give those 8.5s. The 17 has it in a position of 11 all by itself. The 3 18s, I want to give those 13s. The 2 19s, I'll give 15.5s. The 2 20s, I'll give 17.5. And these positions are held all by themselves. Okay, now what I want to do is I want to come in and add a column here. And now I want to come in and actually give the gender. So I have a male, and this would be a female. The 14 came from a female. The 15 came from a male. Doesn't really matter. The two females were 15. Two 16s came from female. Two 16s came from male. 17 was a male. The 18, one was a male and two were females. The 19, we had one of each. And the 20s were one of each. The 27 was a male, and the 35 was a male. Now what I want to do is I want to sort these. But I want to, have the values according to gender, and okay, this over here is going to be kind of irrelevant. So, I want those sorted across by males and females. Okay. Well, the next thing I do is I come in here and I want to go. I want to sum up my ranks. So if I come here and sum up the ranks for the males, I get 119.5. And if I sum up the rank for the females, I end up getting a 90.5. So the logic behind the test is this. If we rank things and there's no difference, then we would expect the average rankings to kind of be the same. If there's a difference in the mean scores, then we would expect more males or females to be clustered around lower scores than the other. But if we have equal means, then we would expect that the rankings would be about the same. High scores pretty much equal, males and females. Low scores, when we rank them, see about the same number of males that we do females. So the next thing we have to do here is we have to come in and do what's called correct for the mean responses. And as I look at this right now, this total sum ranking is 119.5 for males, and it's 90.5 for females. So the sum of the ranks appears to be kind of similar. But what I need to do now is I need to come in and correct for the number of people in each group. Now, this is not a huge deal if we've got equal sample sizes across, like in this situation, males and females, where we have 10 of each. But if we have larger groups, if we get in a situation where we have lots of ties, if we have kind of a crazy difference in sample size, then this could really make a difference. So what we want to see here is we see that we have 10 measurements in each. So let me go back to the. I've probably lost it by now. Yeah, it kicks me out. So what I want to do here is, let me get this straightened up here. All right, here we go. What I want to do, because I have n equal 10 in each group, I want to come up with a mean ranking. And guys, a mean ranking is just the sum, having n equal 10. It's just the sum from 1 to 10. Now we should know, we could easily do this on the calculator, but we also know that the sum of n numbers can be found by taking n times n plus 1 over 2. So in this case, we have 10 times 11 over 2 gives us 55. Okay, so that's the mean ranking. We had 10 rankings in each group. So if we take the mean of the ranking, we just pretty much just find the sum of the rankings. So what I want to do now is I want to come in and I want to take this number and subtract 55. And I want to take this number and subtract 55. So these two numbers right here are candidates for our F statistic. And it turns out that the process that we typically use here is to take the smaller of the two. So I'm going to go ahead and say our test statistic okay, let me get back over here. Our test statistic was the, well, I forgot what I had, 35.5, is that right? Yeah. Our test statistic is the smaller. Of the two. So guys, 35.5 wins out as our test statistic. Now, sometimes, I don't think it's going to happen to us, but sometimes R gets a little bit wacky on calculating this. But I think, well, we'll just have to wait and see what happens. Now, calculating the p-value gets really crazy. In fact, it gets extremely wacky. And what you have to do here is you either need to implement what's called a Monte Carlo method. And if you think about Monte Carlo, I always think about it kind of as at least in the same breath as bootstrapping. Monte Carlo is more of a nonparametric. It allows us to resample using the data that we've collected, assuming nothing about the underlying probability distribution. Bootstrapping allows you to take random samples, but the distinction here is we use our sample estimate to kind of make an estimate of the parameter, and that we pull our samples from that distribution. So this one is distribution free. Bootstrapping assumes an underlying distribution. So it would make total sense that we would do something like this, a Monte Carlo method, if we were going to calculate the p-value. Now guys, I'm not going to get into that here. We're going to let R do those calculations for us. So guys, at the end of the day, if there's no difference in feelings, whatever we're measuring here, across gender, then we would expect the sum of the ranks for males to be pretty close to the sum of the ranks for females. If there's a drastic difference in the sum of the ranks, then we may indicate that it may indicate to us that there actually is a difference. Now, again, this the procedure that we're using here. The Wilcoxon rank sum test works on this principle. And it works on, again, on the principle that if the rank sums should be pretty close if we have no difference. All right. Now let's get things loaded into R. So the first thing I need to do is go back and kind of clean up my data a little bit, okay? And here's what I want to do. I want to, I'm going to clear all this stuff out. So just remember 35.5. And I want to clear this out. And I hope that's the original data that I had. I believe it is. Yes. Now, the first thing I need to do is get this thing ready for R. And I'm going to call this feeling, or just feel. And I'm going to call this gender. So my measurements here are going to go in this column. And my measurements here are going to go in this column. So all I'm doing now is getting this thing ready to take to R. Now all of those are males. And all those are females. I'm going to delete those, and then I'm going to just save as. Let's go Wilcoxon. Okay, what's going on here? Why did it start jumping around? Let's go Wilcoxon revised. And I'm going to shut this down because I don't need it anymore. Okay. Let's go into R. Now I'm going to tell you something we're going to need. We're going to need the car package. So I want to go ahead and do library of car and get that installed. If you've installed it before, that's all you have to do. If you haven't installed it before, then you've got to go install .packages car to actually get it installed. So what I want to do here is just as I always do. I'm going to set my working directory. And I want to go get my data. And this is called Wilcox Revised. And it's not called Wilcox Revised. What's it called? Wilcoxon Revised. Okay, that's cool. Attach our data. Yeah, I don't like long data names like Wilcoxon Revised, but it turned out to work okay. Now, let's say that we're just kind of going from scratch here, and we, we're actually conducting data here, or conducting an analysis here, and we have no idea whether we should do parametric or non-parametric. So, first thing I'd probably want to do is test for normality. So, I might want to do a histogram of feel. And, okay, I have concerns. Next thing I may want to do is I may want to look at the variances. And the variances across male and female appear to be drastically different. Now I could also do a box plot of feel, across gender. And there's not a drastic difference in the IQRs, but there's quite a lot more variability in male scores than females. All right, you guys are going to love this. Okay, I've been kind of saving this up till now. Let's formalize this method. So first of all, let's check for homogeneity of variances using Levine's test for homogeneity of variances. Now guys, I'd say if you did an exhaustive search of the literature and looked at the most commonly reported statistic for homogeneity of variances, I don't think it would even be close. I think Levine's would probably be one, especially in education and social sciences. I think this has a lot to do with Levine's being the default for SPSS, and SPSS is a commonly used statistical software package in education and the social sciences. So I'm going to show you how to do this, but first of all, the null, it would be that we have equal variances. And the alternative is not equal variances across gender. So if we get a statistically significant result here, we're going to assume, we're going to reject the null, and we'll assume that we don't have equal variances. I think from this right back here, the 5.2 and the 443.6, I think it's pretty clear what we're going to get. But it's going to be much easier to report this by conducting the Levine test. So guys, the Levine test, very, very simple to use. It just takes our Y value, which is field, and takes it over our factor, which is gender. And the default here is, well, I'll tell you what, I want to go ahead and just run this and show you what happens. Now, Levine's test for homogeneity of variance, it by the default uses the center as the median. But if you think about it, variance and standard deviation are built around the mean. So I don't like that default. I like field across gender, where my center is going to be equal to the mean. Now, it actually turns out that, and I think this is because of such a small sample size, that we don't get a difference in variances. And again, you look at that and you think, how can that be statistically significant? Well, we've got a small group. We've only got a sample size of 10 in each. And to make things really kick in nicely, we typically need sample sizes of 25 or 30, or even hopefully more. The next thing I want to show you, let's test for normality. And what we're going to learn to start to use here is Shapiro's test for normality. Now, in this situation, the null hypothesis is the distribution is normal versus the alternative, which is the distribution is not normal. Okay? So the way this happens is we do the Shapiro test, and we look at it just across our field. Now, if we do a histogram, and we may have already done this, yeah, we did, of field, you can see that it's kind of a stretch of the imagination to think that that did come from a normal distribution. Shapiro's test of normality backs us up on that. It supports us. We get a p-value less than 0.05, which again is this crazy threshold that we all seem to buy into, which leads us to reject the claim that this distribution came from a normal distribution. So of the two assumption underlying a two-sample t-test, the violation appears to be, I guess, the most intense for the normality test. Now let's do this. Let's run a t-test of field cross gender. And if we do this, again, I wouldn't advise this, but I just want to show you what we would have done if we'd gone ahead and just said, you know, heck with it. Assumptions aren't that important. Let's just violate them and just go ahead and run it, our unpooled samples t-test. We would see that we get a confidence interval that contains 0. And we get a p-value that's greater than 0.05, so we do not find statistical significance. Now, let's do it the right way. And the right way here would be to run a nonparametric analysis. Again, not as much, in my opinion, what we found from the Shapiro normality test and Levine's test for homogeneity of variance, but from just the fact that we realized that we're collecting information here from a Likert scale. And there's no reason to think that a Likert scale is going to be collected from a normal distribution. So what I want to run here is I want to run my model. And we run what's called a Wilcox test. And you'll see that the way we run this is very much like the way you run an ANOVA, or even the two-sample t-test that we ran just previously. We run field, cross-gender. And let's see. I need to put in paired equal false. I don't want to run that paired t-test. And I need an exact calculation to be false as well, because we did have some ties. Now when I do this and I run my model, you can see that we get a 35.5. That's the smaller of the two, kind of the averages of the rank sum, if you will, or the sum of the ranks, subtracting out the mean correction. And you can see that our p-value 0.2861 leads us to fail to reject the null. So guys, we're not finding anything here in terms of differences between the way that males and females feel about whatever we're taking a look at here. Next thing I want to do is get into the effect size. And the effect size is a little goofy here. It's first of all, it's not goofy, but it's extremely important to report, because it's a standardized measure, standard measure, if you will, that's easily comparable. You know, we can't compare ACTs and SATs because they're from different distributions, have different parameters. But if we would find the z-score of each one, so let's say someone scores a 25 ACT and someone scores a 1200 SAT, we could standardize those and find z-scores so we could actually compare those. That's kind of what effect sizes do. They create a standard measure that would be really nice to be able to compare to maybe. I don't know, can I stretch in here? Let's say we found something else in the literature, and they report an effect size and we report an effect size. Well, we can compare those because they're standardized. Unfortunately, R doesn't calculate the effect size for a non-parametric analysis, but it actually turns out it's extremely easy to do. The effect size we use, R in this case, is nothing more than the standardized p-value divided by the square root of our total sample size. So it's going to be something really, really, really easy to find, okay? So the way that we look at this typically is we say that r is equal to z divided by the square root of n. And what is z? It's just the value from our distribution that corresponds to the p-value. Now let me get back over to the blackboard and try to make this make a little bit more sense. So, guys, what we've got here is we have a p-value of 0.2861, right? Yes. But because we I'm having a hard time getting this thing where I want it. Because we calculate our p-value on a two-tail, we know that these two areas had to add up to 0.2861. So what I'm going to be looking for is I'm going to be looking for half of that. So this area here, let's just call that A1, and this area here, the sum of those added up to 0.2861. But it's going to be much easier if I can just take half of that and say that I have 0.143 in each tail. Now you should know by now in a normal distribution using R that we could go, and also it's going to be in both tails. So if we want to find, this is going to be the negative z obviously, and this will be the positive z. What I could do is I could come in and just use the Q function for the normal distribution. I have 0.143 with a mean of 0 and a standard deviation of 1. So gang, let's go do that. So 0.143. So Q norm 0.143 comma 0 comma 1 gives us negative 1.066938. So that's the z-score that corresponds, and I'm just going to use the positive of that. So our R value is going to be 1.066938 divided by the square root of 20. So our R value here turns out to be 0.23. Now remember the thresholds, or not the threshold, remember the, for R, 0.1 is a small effect. 0.3 equals a, let's just call it a medium effect. And 0.5 equals a large effect. So our effect size here is, you know, not quite at the threshold of medium, but you know what? It's I'd have to call that a small effect. So really, not a lot going on. If we were really interested in comparing feelings across males and females of whatever we're trying to measure here, you know, not finding much difference. All right, guys, let's write this up. Now, in a nonparametric test, when we write up the results, we also want to include the median So I'm going to do that. I want to come in first of all and do t-apply. So field, gender, and for median. So the median for male is 17.5, the median for female is 16.0, and I'll use that in my write-up. So guys, I'm going to write this up, and this is an APA style. I would say something to the effect that feelings about, you know, I don't know, whatever we're measuring here, across males, and I would go median equals, what, 17.5, in females. Do not differ. Well, let's say. I'll tell you what, I don't like the way this is going on. Let's let me go back over here. Differences in feelings for whatever we're measuring. For males and females is not statistically significant. And then I'll come in and report my W. It was 35, yeah. And my p-value, 0.2861. And I will report my effect size as 0.239. And that's all you would need to do to write this up in APA style. All right, gang. On a kind of a related note, let's say we had repeated scores, and so the equivalent of the matched pairs t-test in parametric, in our parametric test, is the Wilcoxon signed rank test. So again, we use the Wilcoxon rank sum test when we're comparing two scores that are independent, and but we use the signed rank test. I don't think I'm going to get to demonstrating that. I think as I look at the schedule for the rest of the semester, rest of the summer, we've still got a lot of stuff to go over. So, so guys, that ends this video. And again, this is just kind of an introduction to non-parametric test. What I'll do in the next video is I will give you the non-parametric version of ANOVA. So, guys, have a good one.